Hi students, have you ever noticed that a compass always points in the same direction no matter where you are? Whether you are in India, in US or in Dubai, the compass needle never gets confused. Now, why does this happen? The answer is surprising. Our earth behaves like a huge magnet. But how can a planet become a magnet? Let's find out. The answer to this lies within the earth. So let's look inside the earth. The innermost part of earth is the core, and it is about 1500 miles thick. Both the inner and the outer core consist primarily of iron and nickel. They are extremely hot with temperatures ranging from 4000 degrees centigrade to 5000 degrees centigrade. The inner core is under high and intense pressure which keeps it solid despite high temperatures. And the outer core, which is in liquid state, is about 1300 miles thick. Both the inner and the outer core consist primarily of iron and nickel and are extremely hot. So this iron and nickel, they are in the molten state. Above the outer core is the mantle. So most of the earth's volume is in the mantle. This layer is about 1800 miles. It is composed of dark dense rocks similar to oceanic basalt. The deeper you go inside the earth, the hotter it gets. Okay. So after the mantle, we have the crust. So the crust is the outermost part of the earth. So the continents and the oceans, they are basically on the crust. Now between the inner core and the mantle, we have the outer core, which is completely in liquid state. Now this ranges about 1300 miles. The outer core consists primarily of the molten iron and the nickel at very high temperatures. Okay. We know that the earth keeps rotating around its axis and it also revolves around the sun. This rotation of earth creates a big churning effect in the outer core. Due to this churning effect, huge waves of molten metals are formed within the outer core of the earth. As the metals are in molten state, they are basically ionized. So this flow of ionized metallic ions gives rise to huge amount of current flowing through the outer core of the earth. This is also known as the Coriolis effect. So this is how a huge amount of current keeps flowing within the core of the earth. So the factors which are responsible for this current generation is huge amount of iron and nickel present in the core, the very high temperature of the core, and the rotation of the earth on its axis. This is also known as the geodynamo effect. This geodynamo effect is self-sustaining and it keeps generating huge current in the core of the earth due to the rotation of earth. We know current flowing through a conductor produces magnetic field around it. Similarly, the current which flows through the core creates a huge magnetic field around our planet Earth. If you see this diagram, the blue circle is our planet Earth and the red line is the Earth's axis. At the top of it you can see the true North Pole or the geographical North Pole, and at the bottom we have the true south pole, which is also known as the geographical south pole. Just beside this red line, we have a yellow line, which is the Earth's magnetic axis. At the top of the Earth's magnetic axis, we have the Earth's magnetic south pole, and at the bottom we have the Earth's magnetic north pole. Earth's magnetic axis and Earth's geographical axis, they do not coincide with each other. In fact, they are few degrees apart from each other. Roughly they are 11.5 degrees to 17 degrees apart from each other. We also see the polarities of geographical north pole and the magnetic north pole are opposite to each other. The magnetic south pole is just beside the geographical north pole, and the magnetic north pole is just beside the geographical south pole. These magnetic poles are not fixed at one place like the geographical north pole and the south pole. They keep moving either close to the Earth's axis, or sometimes they keep far away from the Earth's axis. Because of this shifting nature, the magnetic poles are also known as the wandering poles. Now, let's learn about the geographical meridian and the magnetic meridian. So, the geographical meridian is an imaginary vertical plane passing through the Earth's geographic poles, representing true north and south. And the magnetic meridian is a vertical plane passing through the Earth's magnetic poles, aligning with the direction of the magnetic compass point. The geographical meridian aligns with the Earth's axis of rotation. It dictates true geographical north and serves as the foundation for global longitude lines. The magnetic meridian aligns with the Earth's magnetic axis, which does not perfectly coincide with the geographical axis. The Earth's net magnetic field lies entirely within this plane. Now let's understand the angle of declination. Because the magnetic and the geographical pole are offset, the two meridian plane intersect at an angle. This angle between the true north, geographical meridian, and the magnetic north, magnetic meridian, is called the magnetic declination, or the angle of declination. The angle between the magnetic lines and the horizontal plane of Earth is known as the magnetic inclination. It is also known as the angle of inclination or the angle of dip. The Earth's magnetic field, known as the magnetosphere, acts as an invisible shield that deflects streams of charged particles known as the solar winds. When the sun emits a constant flow of hot plasma, the charged particles slam into Earth's magnetic field. This compresses the magnetic field on the sun facing side and stretches it into a long tail on the night facing side. Because these particles carry an electric charge, the magnetic field exerts a force that changes their direction, effectively redirecting the vast majority of the solar wind around the Earth. While most of the solar plasma is safely deflected, some charged particles become trapped within the magnetic fields. The magnetic field lines act as funnels, guiding these entrapped particles towards the north and the south pole. As these highly energetic particles collide with gases like nitrogen and oxygen in Earth's upper atmosphere, they excite the gas atom, which emits beautiful glowing lights, which is known as the auroras. Now these auroras appear both on the North Pole and the South Pole. Now without this magnetic shield, the Earth would likely face a similar fate to Mars, whose atmosphere was slowly stripped away by the solar winds billions of years ago, after its magnetic field disappeared. So we are lucky that our Earth has a magnetic field and it is acting as a protective layer from the solar flares or the solar storms. So students, if you like this video, please share and subscribe, because this is the greatest motivation for us. Thank you. See you in the next video. Bye.